of drugs and rock and roll, and really how this, what this can teach us, what we can learn about scalability within software development. So, I guess why this talk? So for the last decade or so, I've been working in drug development for the pharmaceutical giant GlaxoSmithKline, taking projects through from development into manufacture. So along the way, I've learned a fair amount about what it takes to take projects through from development into production. And then I've also been out live coding music and managed to get around a load of tech conferences. And when there, speaking to programmers about what they do, and realizing that many of the same concepts, many of the same issues that we face in drug development, we also face within software development. So I thought it would be kind of fun to talk about what we can learn in one discipline from what we see in another. So before we start with that, a little survey. Who here enjoyed magic shows when they were a child? Okay, so a fair amount of you. If you will, just humour me, get back into your childlike self, and we'll just have a little magic show. Hopefully you can see here. We take some sort of a magic potion and put it into 3 identical glasses. So one goes purple. Another with luck you can see is a somewhat different colour. And with a little bit of degree of pokery, we can make a nice aquamarine turquoisey colour as well. So, thank you. Thank you for getting your childlike self. So when we do this in front of, taking this into schools in groups of 5, 6-year-olds, and they're like, wow, that's amazing, that is magic. But I don't like magic, and I guess one of the key things that I want to talk about today is that there is no magic. We want to be able to understand things. So in science, there is no magic. And it's the same in programming. It may sometimes look like it. And when I first started in programming, I seem to be bombarded by magic every day. But it's not really there. It's just a lack of understanding. What do we need to understand in order to get through it? And in the same way, being able to scale something successfully into production from development is also not magic. There's things that we can learn and things that we can do to try to make sure that we are successful, or at the very least that we're not catastrophically failing. So that's what we're going to cover today. First up, the chemistry. So this little compound here is called popolahuanone. It was something that I focused on during my PhD. With a bit of luck, this link will get us through to a 3D model of it. And logic. And the reason why the project got funding, as is many of the ways you have to demonstrate its use to the wider field. So this compound had been isolated from a marine sponge in tiny quantities, but had shown in assays some anti-cancer property. So the hypothesis was that the middle section here, which hopefully you can see is planar, that can intercalate the DNA and disrupt the tumour growth. My focus was around these more 3D parts of the molecule, and I developed some asymmetric Diels-Alder methodology to produce these enantiomerically pure cysteclins. And I could talk to you about the chemistry of it, but like I was finding during my PhD, you soon lose people, or they're not interested. So what can we do to try and, gain understanding between disciplines, understand the issues people are facing, what we can learn from other people, and so, move our research into other interesting and exciting areas. So hopefully things will come back behind me. So the chemistry was great, explaining it to other people. It turned out getting the intricacies across was kind of challenging. And it was really the same moving into drug development. People get the idea that you do a bit of chemistry wizardry, throw a few things in, obviously a Bunsen burner, because we all use Bunsen burners at school, right? They're going to have some nice colours, maybe some sparks and things. And after you've done that, I'll pop some magic pills that is going to, hopefully, do some good. So again, getting across what is actually happening in the chemistry, how we manage to get it into production without using magic, It's something that can be challenging, but if we do it, we end up talking to a whole load of different people and learning things that will improve our own craft. One thing I found useful for this was a TV show. Anyone watch Breaking Bad? Okay, so one, it's a cool TV show, and secondly, it's actually pretty accurate with the science. It doesn't tell you exactly how to make the meth, but it is pretty accurate in most of what it's doing. If you've not watched the show, let me just see. You can't see it very well here. This guy, where's the button gone? It is on. This guy here, Walter, he was a chemistry school teacher. He found out he had cancer. He wanted to fund his treatment, and he decided the way to do that was to make crystal meth. He got someone else, a previous student of his, Jesse, involved, partly to help with the hard work in making it, but also to help on the distribution side of it, of which, he was limited in experience. So again, working with others, pool your skill set, it helps. And so what can this teach us about the drug development process? Well, when they started, they just used equipment that came from the school lab. It's pretty impressive equipment for a general high school lab. These are 5-litre flasks. They've got heating from the bottom. You put chemicals in, do your wizardry, and then out will hopefully come the product that you want at the end. So when you're in this stage, just on a small scale, I guess you can get away with experimenting more. They're somewhat limited in their personal protection equipment that you're using. There may be a bit more ad hoc in how they're doing things. But they're there, they can watch it, they can react to what's happening, and hopefully get out what they want at the end. So that's how they got started. But there comes a limit to this. Okay, so if you're selling to a few people, fine. What if suddenly you've got big drug lords wanting, tons of the stuff, kilos of the stuff? You're going to get limited on what you can do. So here they are. I think this is probably around the final product that he's got in a flask, and he needs to decant it out. And you can see, unless you're super strong, you're going to struggle to go much bigger than that. And certainly it's not going to be safe to. You're also limited on throughput. This is Jesse drying the stuff, so he'll get the crystals out at the end of it. But first he has to dry it and remove the solvent. So to do that, it's effectively in a tray, just thin, and it may take 24 hours or so to dry. So if you want one batch of tens or hundreds of grams, fine. If you want to have kilos and kilos of the stuff, and you're limited to one tray or one oven, it's going to take a long time. If you want tons of the things, you're going to have bubble fields, full of the stuff, which isn't going to be so easy to conceal. So we obviously have to think about the equipment that we're using as we scale things further into production. And so actually what they did on Breaking Bad was moved into equipment that is really quite similar in the way it looks to the pilot plants, the test plants that we use in drug development. So you'll have a vessel here where the chemicals go in. Rather than hand spooning solids in, they'll get put in through the top, and you'll pump liquids around. But there's an awful lot of things that we need to consider in order for our chemistry that works in the lab, in development, to work the same when we go up into production. So, for instance, just quickly, how do we get materials in? If we're just adding a spoonful of material, it's quite easy. We only have to open the vessel for a moment and do that. If we've got bags of the stuff, we've got more difficulty getting that in. There's a lot of weight, and it's also going to take longer. And the chemistry may well be affected by how long it takes to add the materials in. One of the big changes is around temperature control. So in a small flask, you've got a high surface to volume area, so you can be quite efficient in getting energy in and removing energy from the system. As you go up in scale, that surface area to volume decreases and means the efficiency of heat transfer is a lot lower, which means it's going to take longer to heat things and longer to cool things. And if your reaction's giving off a lot of heat and you've not got control of it, it's going to run away and you're going to potentially have a serious problem. You also probably want to put in more controls so you can make sure that things are happening the same way, and you're going to need to make sure that the operators of the equipment are in a safe place. So in this case, being safe from all the fumes and other chemicals. So what happens if you just taken your process that you were running, so the chemistry that you were running in simple equipment and development, what can happen if you take that through into production without understanding what is actually happening? I guess there's been countless examples in the news. This was in Louisiana a year or so ago, where if you haven't got control over the process, you can have a catastrophic failure. It can be serious, it can be fatal, and obviously something that we need to avoid. We need to understand what is happening. So not just in the chemistry, but what is happening as the process. So how the chemistry is affected by the environment that it's in. So in chemistry, we can avoid these sort of catastrophic failures as we're scaling up into production, basically by understanding exactly how the chemistry works and how it is impacted by all of the environmental factors. So things that we've just mentioned about the rates of heating and cooling, rates of additions, the equipment that's used, efficiency of mixing, how easily gases are released, the quality of the inputs. The input that you get on a small scale, you may not be able to get from the same supplier on a large scale, and that may well affect how the chemistry runs. And also things like the availability and the ability to safely handle the materials. So there's a whole range of things that we need to understand in order to not have those sort of catastrophic failures. But we also need to understand that there will be failures at times. Particularly if there's operation by humans, there will be errors. And there will also be times when things go outside, equipment failure, for example, outside of the ranges that we wanted. So there will be failures. What we need to do is understand what are those potential failure modes and make sure we've got mitigation plans in place for them so that we constrain our failures to something that may affect one user, one batch, one plant, but it doesn't take out everything. So an example of this in chemistry may be the vessels they contain, they're under an inert gas. They're effectively sealed to avoid the chemicals going out into the plant. But they will have pressure release valves. So if the pressure builds up for some reason, because the chemistry's run away, it's not gone as planned, rather than going up like a pressure cooker until the whole lot explodes, it will slowly release so that it will maintain a safe situation. So your batch may fail, but you haven't blown up the plant. So what about scaling code? We're hopefully not going to have too many plants exploding, but we can still have catastrophic failure. So I'm here at 8th Light in order to understand many of the things that we need to control. But the fundamental is that we need to understand what is happening, understand what can happen, and make sure that we constrain any failures to limit the impact as much as possible. So hopefully, though taking out into a chemistry situation, the idea that we need to consider how what we're doing in development works within a wider environment doesn't come as great news or too much of a shock. It's something that we know things are going to behave in different situations and we need to account for that. What about the control of the quality? So in drugs, going back to Breaking Bad, Walter and Jesse's hallmark of quality was the fact that they got blue crystals out. So their customers knew that they were getting good stuff because it was blue and it was better than everyone else's. As an aside, it's an absolutely atrocious quality mark for any drug. So you can have parts per billion of something that's going to affect the colour. There's no way that crystal meth should be blue. And they were just, I guess, lucky in the fact that they kept on getting the same colour going through. There was something in the way they ran the process, or more probably one of the materials that they used that impacted on the colour going forwards. But their sign of being consistent was they were getting blue material out, and that gave confidence that the quality they were getting was the same, going from their lab up into plant and from batch to batch. So, how do we actually control the quality and determine the quality within drug development, within chemistry? I'm going to take you on a little coding experiment for this. But first of all, I guess just the note that we never have 100% purity. So in chemistry, no material is ever 100% pure. There is always going to be some sort of impurity in there, and that can change from batch to batch. So let's just explore this with a bit of simple code. We're going to define a reaction, a simple reaction. We'll call it RXN reaction. And this reaction is just simply going to take an input, and as its output, so the input in this case is just going to be an integer, and it's going to return the increment of that input as the output of the reaction. So, a little bit of Ruby code, defining our reaction, taking an input as a parameter, the output, input plus 1. Nice and simple. So, we make the method call with the argument of 1, and we get 2 out as the output. So nicely, we're going from 1 input to 1 output. 100% pure is easy. So we define a reaction, chemical reaction, a model of that, and it's just going from one thing to the other. But I've already said it's never that simple, never 100% pure. So what if we make our reaction depend on a local variable? So we're going to say the course of our reaction depends on the temperature that's at the reaction. So we're just going to put in the local variable temp, and I'm setting this to 20 plus a random number, so rand 50, a random number from 0 to 49. And then putting in a conditional, so the temp's greater than or equal to 60, so that should happen 10 out of the 50 times. We're going to say it's too hot, it's doing something more than we wanted. We're going to get input plus 2 out rather than the input plus 1. But if it's between 25 and 60, we're going to get our desired result. So 35 times out of 50 on average, we should get the desired result. But if it's less than 25, so we're saying if it's too cold, it's not going to react, it's just going to return the input. So now when we call reaction 1, we're either going to get 1, 2, or 3 out, depending on the value of that local variable. So again, this sounds pretty easy. Okay, let's set the temperature to 50. It's going to give us what we want. Straightforward. Apart from when you consider what is actually happening. So when we have a reaction, it's actually billions and billions of reactions that are going on. So if you consider water, for example, 1 litre of water contains somewhat just more, I think, than 3 times 10 to the power 25 molecules. So if it was water that was reacting, each of those molecules would be doing the reaction, and they're each seeing what is local to them rather than the bulk. So they'll all have discrete local energies, local temperatures, which is not necessarily the same as the bulk temperature that we've set. So if we go back to the code to look at this, we can set in a new array, call it reaction output, and what we're going to do is we're going to compute 3 times 10 to the power 25 times this call to reaction with the input of 1. And then the output we're going to put into our array. So now we end up with an array containing 3 times 10 to the 25 elements, and it's going to be a 1 to 7 to 2 mixture of 1, 2, and 3. So if we just want 2 out, we're going to have to do some extra processing. So in this example, it's going to be pretty easy. We just add a filter on the end and we just get 2. So no big deal. But what if, instead of being some simple function, what if we had something complex and it required some really intensive processing in order to get out what we want? It's obviously going to add extra processing time, processing power, and it's going to increase the risk of errors and bugs and things going wrong in the future. So ideally, we'll want to avoid this extra processing. And it's exactly the same in chemistry. If we get a mixture out, we're going to have to add some extra purification steps, which sometimes are fairly easy, sometimes are almost impossible. And every time it's going to add extra cost and time and places where things can go wrong. So what can we do in order to minimize the amount of extra processing that we have? So we can design our reactions to be more robust, for them to be more tolerant of the variation that we can see, so in this case with temperature. So effectively the same code as we had before, but we're now calling it our modified reaction, still taking the same inputs. Our local variable is the same because we've not done anything in terms of how we're controlling the bulk of the reaction, but we have changed how the reaction works, how tolerant it is. So now only one time out of 50, when it's greater than or equal to 69 the temp, is it going to be too hot to do what we want. And only one time out of the 50 is it not going to have enough energy to react and just give us the input. So now anything which is between 21 and 68 will give us our desired result. So we've modified our reaction, we've made it more robust, more tolerant to the variation. So now every time we call this reaction, we've got a 96% chance that it's going to give us what we want. So our overall array of output molecules is going to be 96% the right thing. So not 100%, but things don't necessarily have to be 100%. 96% may be good enough either as the end product or as the next step in processing. So how do we practically look at increasing this robustness, this tolerability? Don't know whether anyone recognises this. It's from a picture from the UK. This is Striding Edge in the Lake District. If you're actually there, it feels a whole lot more dramatic and real than the picture represents. But there's a path that goes along the middle, and on either side there's almost sheer 1,000-foot drops. So if you're walking along, you follow the path, you're absolutely fine, and you'll reach your destination. But you take a wrong step either side, and you're off the cliff. And they're pretty catastrophic results. So what we don't want is our chemistry to be in this sort of situation. You know, we don't want to say the temperature's at 50, but if at 49 it does something else completely different, and at 51 the whole thing explodes. We don't want to be in that situation. We want to be more in the situation of this road where we can, assuming there's no trucks coming along, we can just meander along the middle. We stumble, we're still on the right path. Even if we go a long way from where we should be, we're only going in the sand on the edge. Maybe a little uncomfortable at worst, but we'll be able to recover and get back on and still reach our destination. And so, I guess, the same as chemistry, that's where we need to be in terms of our software. We want it to be able to tolerate the types of inputs, the type of equipment, the entire environment that it's going to be subjected to when we release it into the world. We want it to not fall apart if someone puts in a wrong number or puts in a space in their password and the whole browser then just dies. It needs to be able to recover from it. So we want to have our system, have our process to be able to be tolerant of everything that it could possibly face. And that way it won't fall off a cliff. So we had our simple reaction. We've just got the single input, and it was only concerned about the temperature. But in the real world, there's obviously a whole lot more going on, so consider the effect of, for example, pressure, mixing, the equipment surface, and a whole load of other things. You also need to consider what happens to the output. So you've done a reaction, you've got the output, but that's still within the reaction mixture. Is that going to inertly sit there, or can that react on as well? So if you think about a simple code example, we put in 1 and it gives 2. If that's still in the mix and that can be taken into the function again, it's going to carry on processing, and we'll end up with more and more higher numbers, more and more different components in our mixture. And not only that, the presence of the output may affect the course of the reaction. So if you think of an exothermic reaction, one that gives out heat, if one molecule reacts and gives out heat, how is that going to affect the molecules around it? It's going to see different conditions than it would have done if that molecule hadn't reacted. So you've got a complex system that's dependent on all of the other billions of things happening around it. And then we don't have pure inputs. In our code case, we were putting 1 in, but we're never pure. There's going to be some sort of related compounds, maybe trace metals that are going to change the course of the reaction, water, inorganics, different solvents. So they can change the course of the reaction, change what our outputs are, and they can also react themselves. Maybe they'll stay as they are, and you'll just have the impurities that you had at the start coming out in the end, but they could also react on. And then what happens if we have multiple inputs? So we have A, B, and C all reacting together to give D. And then we're going to take D and we're going to put that in another reaction. And what would often be the case, looking from crude starting materials going through to a drug, you can easily be putting 20 or so of these reactions together, each one having dozens and dozens of variabilities. And so you end up at the end, you've got thousands of different components that you may have to worry will be in the final product. So how do we guarantee that we've got the quality? So if you're making a batch of meth like you do in what are you going to do? So you could just test it all yourself. So if you're just making a little bit and you're that way inclined, maybe that'll work, but there are certain health risks associated with it. If you were suddenly to be making tons of this stuff and you were having to test every batch, then obviously those health concerns are going to go up somewhat dramatically. And what about your customers? So I guess, if you make a first batch and you just share among friends, maybe they're willing to take that risk that, maybe it's not good, maybe it doesn't have the desired effects. They've not paid anything, you've just given it to them, they're going to take that risk. And so maybe we'll do that with code. Maybe we'll hack out some game and share it with our friends and, it doesn't work. Who cares, We'll just give you some grief that it doesn't work, maybe help you to fix it, maybe not. But there's no particular big deal. But if you're making lots of it and you're selling it, are you going to test everything that you give out? So if we're making code and we're shipping it to thousands of people, are we going to go to each of their boxes and see whether it works? Are we going to make thousands of batches of meth and try them all out ourselves? So it's something that isn't scalable. It can be useful at times, but certainly not scalable, and certainly not something that we can do within the pharmaceutical industry. So what do we do? So we can test. This is what they did on Breaking Bad. They take the material at the end, they show it to some magic machine. It blinks for a little bit, and then it gives you some sort of a magic number. So Breaking Bad, like in our previous code example, actually, they had a magic value of 96% they were trying to hit. So if it was 96% or higher, they knew they had good stuff, they were okay. It was going to be of the quality they'd agreed to give to their customers. If it was less than that, if you were down anywhere less than that, down in the 70s, for example, you know that something's gone wrong. It's not good stuff that you made, and you're going to have to do something about it. Either more processing to try and purify it, or just get rid of the batch and start again. But of course, machines that just magically give you a number don't exist. In chemistry, we'll get those off. We'll tend to do a whole load of orthogonal analysis, but they'll often give you chromatograms like this, where you've taken your output, which is this mixture, and you somehow separate it across some other phase. So a typical one would be to make a solution and some solvent of your output, and you can pass it through some other phase, maybe a stationary phase, where the different components move at different rates depending on their affinity for either the liquid or the solid. So this means you end up having a plot against time and response. So the response could be anything. An example would be it's the UV absorbance of the components at a certain wavelength. So you pass the output through a UV wave, and depending on what's absorbed, depends on how big these peaks are. So hopefully you'll get one big peak, which is what you want, and you'll get a few small things. So this could be our 96% peak of what we want, and then a few others that are like half, 1%, and some very small things. So now we actually have a reason for starting to believe this number that we get out as our measure of quality. Except do we? So in order for us to actually have confidence in it, we need to know a whole lot more than we just get out from here. So, for instance, we've just run to 15 minutes. What about components that are going through this slower? And you've got another big peak over here that we're just missing. What if there's a peak under this big one? Maybe it's two things the same size in here, and we're just completely missing it. And this sort of thing happens all the time when we start off with some generic test methods, and then we have to explore to see what is actually happening. And then you've got here, maybe this is just so small that you can just ignore it. But what if this molecule doesn't absorb in the UV range that you're detecting at all? This could actually be the major component, and we're just totally ignoring it. And again, this is something that is really quite common. So in order to have confidence in the number that we get as our magic quality mark, we need to make sure that we can see everything that's in there and that we understand how they respond relative to how we're detecting them. So we can do this, we can do all of this for a given batch. We can either isolate or make all of the impurities, see how they respond under the analysis, and actually get a meaningful weight assay out. But what happens if you then get another batch? How do you know that that batch has got the same impurity profile? What if something different happened, and this time you've got another peak here, but it's not, or another peak in here, and our method isn't going to detect it? So not only do we need to know all of the impurities that we know about, we also need to know about all the impurities that we don't know about but are hypothetical. And then for all of those, we either have to give sound chemistry explanations of why there is no way they could actually be in our material, or we have to make them and demonstrate that we'll be able to see them. So when we're talking about a process where there could be thousands and thousands of components in there, if we have to spend days, weeks, months making each one, changing our tests so that we know our tests are going to detect them, you end up having a huge amount of work. So is there anything we can do about that? So one of the things is to constrain the inputs into our reaction so that we limit the variability that we're going to get. So if we limit the variability, if we limit some of the potential impurities that we get out, we then don't need to worry about being able to test them at the end. So we take away a considerable portion of the work that we need in order to confidently say that we're delivering what we say we are. So what does this actually mean? Let's go back to the code example. So let's assume we've got a reaction this time we're naming reaction 3, and it's going to take simply an input, which we're calling C, and it's going to, as output, give D. So we've basically just got a simple reaction, takes C, and does whatever it does to deliver D. So as we've already seen, the quality of D is going to depend on the variables within that reaction, within reaction 3, and it's also going to depend on the impurities of the input. So it's going to depend on the input that goes in. So we need to be able to test D to ensure its quality, and in order to do this, in the chemistry example, we need to understand all of the known and all of the hypothetical impurities. So there's a lot we need to do and a lot that we need to demonstrate. Well, suppose that C can be manufactured in two ways. We've got reaction 1, which is going to take input A and is going to produce our desired output C. And we've got a different reaction. Maybe it's manufactured somewhere else. They convert a different input, but still gives the same input, the same output that we want. So we know that C is going to have different potential impurities depending on which route it's been made, because it's going to see different inputs and different variables. And so D will have a different potential impurity profile depending on where it's sourced C from. So if we only allow our reaction 3, the reaction that's going to convert C to D, to take in as input C of a certain type, so for example C that has been manufactured through route 1, we're going to effectively halve the number of impurities that we have to worry about in that part of the synthesis. So we're constraining the types into our input, and therefore creating some extra safety in terms of the quality of the product at the end. And to get to this point, we really need to start thinking about how things are going to work in production from an early stage of development, so that we can consider the equipment it's going into, consider the type of variables it's going to face, and we can design a robust process that's going to give us the quality that we want. But even if we've done all of that, things can still go wrong. So going back to Breaking Bad, Jesse at one point got taken off and told to make the meth himself. So he'd been working with Walt. He knew how the process worked. He knew what went in, how to do it. But when he did, he wasn't getting the 96+%. He was down in the 70s or something. So what went wrong? I guess there's two explanations. One, they hadn't got the robust process. They were on that knife edge, and he stepped to one side of it and fell off the cliff. Or there was a transfer of knowledge issue. So there was some way, either in the setup or the way things worked, that was in Walt's head. He knew how to do it, and including that extra bit of information meant that the process was robust and you could always deliver the appropriate quality. But that information was in his head and hadn't been transferred. And so, of course, as we're moving from our lab equipment into production, or from our box into deployment, we need to make sure that the important knowledge is not just in our head, but is spread out to everyone else who's going to be involved. So in order to scale our, if you want to go from here, I'm not advising it, and go home and make some meth, there's various things that you need to consider if you're going to, be a successful drug lord. So you need to think about the whole system. We need to be able to guarantee our quality, so we don't get people coming after us for giving them bad stuff. And we don't want to be necessarily having our hands dirty all the time, so we need to be able to transfer that knowledge to others so they can do the dirty work for us. If you don't want to make meth, maybe you want to make some jam this weekend. Anyone made jam before? Yeah, a couple of you. So it's really quite simple. A bit of fruit, a bit of water, I think, a whole load of sugar, particularly if you've got a sweet tooth. Put it on the stove, heat it up for some amount of time until it goes all nice and thick. Let it cool down, put it in jars, and then spread it on your toast or whatever else. So you can make some jam. So, if you do that this weekend, and it's the best jam ever, and it's like, okay, it's like this code malarkey, I'm going to be a jam manufacturer. What are the things that you need to think about? So, everything that we've covered, is this the same, really scaling everything? The equipment. If we're going to be selling millions of the jars into the supermarkets because it's the best jam ever, we can't do it all on our stove. So we're going to have different equipment. We're going to have to understand how the jam making process works within that equipment. We're going to want, I presume, some sort of constraint on the inputs that we put through. So maybe you just got some blackberries from your backyard, but there's not going to be enough to sustain the production of millions of jars of it. So where are we going to source this from, and how are we going to make sure that the fruit that we source is going to give us the quality jam that we want? And again, you probably don't want to be hands-on making every batch 24 hours a day in order to meet the production requirements. So you're going to want to be able to transfer your knowledge. So I guess what I'm saying is there's a lot we can learn from making jam. What about coffee? Instead of making jam, maybe you've opened your own coffee shop, and it's great. You got your own specialty coffee, load of snacks, great customer service, and it's always busy. And so it's like, okay, how do we make this more profitable? Let's get more people in, but we're constrained on space. So everything we've been talking about so far has really been about scaling up, making more. But how can you do this in this situation? Maybe you can take over all of Trump Tower, make it all into one big coffee shop, and hope that you're going to get thousands of people in the same place wanting to drink your coffee at the same time, and therefore increasing your profitability. You're probably going to go out of business fairly quickly. So maybe you'll think more on the model of, okay, I'm going to be the next Starbucks. So I'm going to put out identical shops on pretty much every corner, but far enough apart that there's going to be enough customers. And they're all going to be modelled the same, so that we've got our brand and we've got our quality and we're going to deliver what our customers expect. but there will be some certain amount of flexibility in there so that those shops can be configured by the local managers. So this scaling out, what does that mean in terms of chemistry, and what does that mean in terms of software? So there's times when we're going to want identical setups. We're going to want to make sure we've got the same thing across different places or across different people. Or we may want some sort of local configurability. So in chemistry, this happens all the time when we're doing experiments to understand the chemistry, to understand how it works with variables, different values. We don't want to do this in production, because if we've got the production pot are limited, and if it takes $1 million worth of material for each run, and you need to do 500 reactions in order to get the understanding you need, there's not many places, including GSK, that's going to want to spend $500 million in order to do that. And so we have mocked down equipment. We have equipment that we can use in the lab that is a mimic of the large-scale equipment, and then when we put our processing knowledge on that, we can have confidence that what we're doing in the lab is going to mimic what's happening in production. And everyone within the team will have access to the same equipment, so an experiment done by one person, you're going to have confidence is going to work the same as an experiment done by another person. So we're not worried that it's the person that's making a difference in the results, and we can have confidence that it is what we've actually changed in the chemistry. And this happens the same in software. So DevOps tools, Chef, Puppet, Salt, are designed so that we can work in development to mimic what's actually going to happen in production. Something I know very little about in terms of software, but I think the ideas are very much the same as it is within chemistry, within drug development. It's about having confidence that what we're each doing individually is going to mimic and work the same as it will within production. So we want to take out some of that risk. So the final thing I'm going to talk about is architecture. Anyone know this place? Falling Water, yeah. Falling Water in Pennsylvania. Frank Lloyd Wright, iconic building. What would happen, if you got the chance to ask him what scalability meant? Do you think he goes, yeah, I built this, now I want to stack 100 of them on top of each other so we're as big as Sears Tower? Which is the scaling up sort of mentality. Or maybe you're thinking, no, I've done one of these, let's just give the design and we'll put one on every street corner, in the country. So there's millions of them. Again, did he build an iconic building so that it looks the same everywhere? Probably not. So maybe what scalability means in this case is a scalability of ideas. So the fact that you can have different approaches in architecture, that you can merge the nature with the angles of concrete. You can put things together in different ways and make something that is different than everything else is around. Make a more enjoyable experience for everyone. So scaling of ideas, it's also something that means that we can start sharing our thoughts, sharing our ideas with others, helping others learn, and also being able to learn from other people. So back to the chemistry wizardry. How could I explain to a class full of 5-year-olds the drug development process? And I figured that talking about Breaking Bad would probably not go down too well. And so instead we made some magic potions, because 5-6-year-olds understand about wizards. They know that they put things in certain orders and certain quantities, and they have the understanding of, if they do that, something is going to happen. Going to make a potion and you're all going to turn into frogs. And it's basically the same with drug development. We're going to put things together certain ways, certain orders, understand what is happening, and then we can hopefully have our desired effect at the end. And so with the kids, got them making potions, and they could then, at the end of it, tell me why these 3 glasses are different colours, why we got purple, and then how we can turn it green and pink, and various other things. So we're using scientific terms to get them to understand in a simple way, and basically take away the magic. If you're interested, this just comes from red cabbage. It's a pH indicator, so it'll go a different colour depending on whether it's seeing acid or base. So it's really quite simple, and it's the type of thing that you can get kids doing, and they can understand a little bit more, maybe inspire them to do a career, subject choices that they wouldn't otherwise have thought about. What about software? This was Strange Loop last year. So playing as part of MetaX live coding closure. So we were developing synths, playing with those, putting it all together live, and we were projecting the code. So this works fairly well at tech conferences. So like at Strange Loop, people are going to be able to see the code, have an idea of what's going on, realise that we are actually doing things rather than just pressing play. But if you're in a non-programming environment, so when we took this to local bars or art festivals, people hadn't a clue what we were doing. They may comment on the interesting or beautiful visuals, but they had no idea what we were doing. There is no way that they could tell that we were live programming the music rather than just pressing play. So we had a constant dilemma of what can we do to show people what we're doing? What can we do to show people that code can be an instrument in the same way as a guitar or a piano? So I guess what we came up with was, if people are going to understand, they need to have an appreciation of what code is, and an appreciation that you can do a whole load of things with it, including making music. And then this got realised through Sonic Pi. So Sam got funding from Raspberry Pi Foundation to build some software for making music that could also be used to help children to understand some concepts of programming. So this met what we wanted. If you get all the children in all the schools in the country seeing more about what code is and some of the things that you can do with it, including music, they'll then see coding as either a potential career path or a potential artistic path to do different things. And so that's what we did. Went out into various schools and other workshops, and you can very quickly start using the audible programming features to start bringing in programming concepts. I've changed somewhat how I go about this teaching since I've started trying to write structured code myself. So when I was first using Sonic Pi, I was using it in a way that I could make music, in a similar way that I'd done with Overtone, trying to mimic what we could get out from that, but not in a way that is necessarily of structured code that you could then transfer through into other environments. But it turns out that you can, and that using the audible feedback gives a very, very quick feedback loop in terms of what the computer program is doing. So you can effectively take a non-programmer, someone who has never coded anything in their life, and within a short session had them writing functions, doing recursive functions, doing multi-threading, and all sorts. And they're getting that constant feedback through the sounds on what is happening. So if I've got time and you'll humour me, I can go through an example of that. So bring up Sonic Pi, which is it comes pre-installed on Raspberry Pi, but you can also download for free on Macs and Windows. So imagine for a moment, which may be hard if you've been in programming a long time all your life. Imagine you've never seen anything, but you do know how to do laundry. Okay? So we're going to code the laundry cycle. So when we talk about the laundry cycle, what's the first thing that we do? Well, I guess we wear clothes. So I'm wearing clothes, so we can. I just wrote this in here before. It'll start blank normally. I just did that as a sound check before. But we can use samples. So if we write in sample, we then get a list of potential samples we can use. So they've got a key name that's going to that's going to link to the sample, so we can choose any of them. Let's choose this drum. And we can say, when we hear this noise, this is representing us wearing some clothes. So if we press play, you can hopefully hear a drum going. So we've worn clothes, and we can wear them and wear them again. So we've got a sound that's going to represent us wearing clothes. So after we've worn them, we're going to want to wash them, the next step. So we can make a different sound in order to represent us washing clothes. So there's various synths we can use, and we access those by writing play. There's a default synth, so if you don't define any others, it's going to use the default synth, so we'll do that. We have to pass it some argument, so effectively the pitch it's going to play. So we can write this in a few ways. We could do something like C3 or A4, but I'm going to feed it the MIDI note, so 60 is the same as C4, which is middle C. So if we now run that, you hear both of them, but the wear and the wash, the sample and the play, you're hearing at the same time. Whereas actually the program's starting from the top and going through, but it's happening too quick for us to be able to hear. So we can put in a pause to make it easy for us, just by sleeping, and then we hear our wear, wash, and we can keep doing that. And after we've washed, maybe we want to dry. So again, we need to put a sleep in, and we can choose a different sample to dry. Let's put a sleep in for that. So now we have our wear, wash, dry. So we've got our laundry cycle. So we've done it once. If we want to do it more times, we could either write it all out again, or we can start doing these put this in a block and repeat it. So Sonic Pi is based on Ruby, so we can do 5 times, for example, do. And you can start talking about blocks. So everything in the block, everything between the do and end, is going to follow the instruction at the start. So it's going to 5 times do. And then our wear, wash, dry sample is just going to carry on repeating. Apart from I missed something somewhere. Thank you. So we have no tests in place for this, so things can fail during production. But at least we've got the audible feedback, so we can actually hear what's going on, and we can start finding where the errors are. So this is going on, not very exciting. And also, we can also align our code so that it makes it more readable. But still, it's hardly readable. If someone else came in here, they wouldn't go, haha, you're coding the laundry. There's no real way to know. So we can start teaching people who not code to start refactoring. So we'll write a method for where, just take out our where instructions and replace it with our method call, and then things sound exactly the same. And obviously we can do this for all of the bits. If I can, I know copy and pasting isn't necessarily the best thing to do, but if we name them things that are sensible, you can start then seeing that we've created a laundry cycle, something that may be that is going to be easier to understand, still sounds the same, but now if someone's coming in, they've got an idea of what it is you're trying to achieve. And of course, what's more, we've now just got single places to go in order to change it. So if we wanted to change our wash to be at a different pitch, which maybe we're using to represent the temperature at which we're washing at, we can just go to the one place and change it. And of course you can then start putting in passing arguments into our functions so that we can reuse the functions in different places. So we'll make wash take temp as a parameter, and again things sound exactly the same if you've done it right, but you've got that extra flexibility. Of course, things aren't necessarily as simple as just doing a simple wear, wash, dry. So maybe you're really messy, and every other day you get your ketchup down you and you've got a stain and you want to do something with it. So you can start teaching them about conditionals, and obviously using language that hopefully as a non-programmer, you're still going to understand the intent of the code, which is obviously what all of us are trying to do. So we just write our functions in the same way. So we can maybe get this to return as a Boolean, where we get, 50% of the time we're going to be dirty. And if we are, we're going to call treat stain, which we're just going to do something very similar as, which we have ambient quiet, that'll do. Yeah, something very similar as before. So now, hopefully, half the time we're going to hear that other sound, the ambient quiet, which is going to represent that we're treating a stain. And there's, the things that you can then do can obviously continue. Let's say that we're going to pass a smell variable to wear, so that we're going to carry on wearing our clothes until they get really quite smelly. So we're going to wear, which is going to take in a smell, and start talking about recursive functions. So let's just say that our smell is going to increment each time, and our smell is going to affect the rate at which we play the sample. So the higher the number, the faster the rate, our sample is going to get squashed. It'll take less time to play, but I guess more importantly, we'll hear it at a higher pitch. So obviously, we know what's going to happen here. We're doing a recursive call with no escaping, so this will just carry on forever. So, of course, it's always nice to see what fails before you show what you can do to avoid it. So let's say if smell is greater than or equal to 9, we're going to do something different. And else that. Let's align it. And sorry, I had to stop the previous run that was going forever. And then hopefully, if we've written our recursive function correctly, when it gets to a certain point, it's going to escape out of it and carry on with our laundry cycle, which is good. And we can obviously then do multiple laundry cycles. So maybe let's just make these for 2 times so they don't carry on forever. So it'll do one and then the other, and we can do these using different inputs. Let's make dry taking a dryer as well. Get electric beep, and what else have we got? Let me just choose something that could be interesting. Let's do that one. Okay, so now when we press run again, we should have 2 different laundry cycles happening one after each other, which is fine. But what if with these laundry cycles are representing what is happening in different houses, and they're actually happening at the same time? Can we get our programs to cope with 2 things happening at the same time? So we can start talking about multi-threading. And so in Sonic Pi we can wrap one of them around an in thread. Let's stop that. And then they should both be happening at the same time. So you can, if you can't hear it, you can see in the log that you've got the multiple things happening at the same time. So we've now got our cycles going on that are making their method calls with different variables. We've got conditionals in there, recursive functions, and we're doing the multi-threading. So already within 15 minutes, you've learned quite a bit, and you're using code that you can then take out into a generic Ruby environment and start thinking about how you can write other things. So instead of making our where function make some sound, maybe we're going to make that control our appliances or call the service up online, so we don't have to worry about doing the laundry ourselves. But then, what if you're actually wanting to use the music for a performance? So at the moment, we can play things, we know where we can change them, but if we start changing things as we're going, it starts up new runs, and then they're all over the place because you've got two going, and unless you're really lucky, they're not going to be in time. So what we've got in Sonic Pi is an ability, using live loops, that's going to look after the threads for us behind the scenes, so we can get rid of this in thread and change these 2 times into live loops, which we're going to call the first one laundry 1, and we'll do the same here with a different name. So now things should sound the same, but now when we change them, something different happens. So now if we change this one to 70, what it does is it redefines the functions, and it checks if the threads are already running. If they are, it doesn't create new ones, so they carry on but with the redefined functions. If the threads don't exist, then they're going to create a new thread. So now we've got the chance of hot swapping the code as we go along, and we can start thinking about how we can move this into more of a performance. So probably didn't need to stop that, but maybe let's run that up again and see what happens if we want to just add more cycles going. So hopefully you can hear me above that noise. It's not the most exciting of music, but let's do something which just makes it sound at the start of a period of time. So let's do another drum sample. We're going to sleep for part of it, and then let's do a different drum. Oops. Sorry. That'll do. So now if we start this, you can see that we've started a new thread, and because it didn't exist, it starts up, but it's not in time with the rest. So again, that's not going to be great in terms of having control of our music performance. But what we can do is start syncing these together so that one won't start until another one's queued. You can sync them to any of these, but it's easier if you sync it to something that you're not going to change throughout the performance. So we just have some sort of a metronome going, which is just going to sleep for a bit, and then we can sync everything in so that all the other loops won't start unless they're in time with the tick that we just defined. And one more. So we can do this as it's playing, and then you'll have a little bit of a blip, but then suddenly everything should be in time, and then we're free to do what we want with the rest of it, and everything stays in time. We can start morphing the sounds that we're doing, putting effects over it, building things up, and hopefully getting something that's more interesting. And if you're in a club, that we have everyone up dancing. So I'm going to leave it at this point rather than getting anything more, but hopefully that demonstrates how you can take someone who's never coded, take a scenario that they all understand, show how we can code that, and you end up with some concepts of programming at least that you can then take out into the real world. So if people are interested, they've at least got a basis and some words that they can talk about in order to follow up on the learning. If you'd like to do it more for performance situations and take it further, then go in, explore Sonic Pi, see what everyone else is doing, and maybe we can have a jam sometime. So coming back to this, coming back to the scalability, we've covered a few things, I guess, in this last hour. So if we're going to scale things, we need to think early in development, what production is going to look like, and what we need to do, what work we need to do in development to give us confidence that that is going to safely scale and that we're not going to have any catastrophic failures. We looked at quality, what that means, and how we can measure it and determine it. So from user tests, working the REPL, just experimenting, through to well-designed test suites where we've thought about all of the possible edge cases and all possible scenarios, and also when it's appropriate to start thinking about the constraints that we're going to put in, how we're going to limit the types of inputs into our functions. Talked about transfer of knowledge, the fact that we need to be clean in our intent and in what we're doing, and some of the times when we need to think about scalability in a different way, making sure we've got consistency of approach across people and places. And then we talked about scaling of ideas, and I guess this is something that is important for all of us as we're honing our crafts, as we're hopefully designing code that is scalable, sharing that knowledge with other people, helping them also to get the same sort of ideas that we've managed to get over time. So hopefully what I've covered is that the science isn't magic. We shouldn't tolerate magic within the programming that we're doing. We should understand everything, and that if we do that, then scaling into production is also it's a skill and a craft rather than magic. So thank you all for coming along today. If you've got any questions, then I'll help out if I can. Thank you. Okay, well, thank you then.